So nuclear fission generates a lot of energy. Where does the energy come from? So this is the nuclear reaction. We've got uranium-235 being turned into barium-140 and krypton-93, and we've got 3 neutrons given off and 1 neutron used to cause this to happen. So if we look at the mass of the reactants and the products, the law of mass conservation says that the masses should be the same, right? And here we're getting very precise with our masses. So the total mass of the reactants, 236.05258 atomic mass units. Total mass of the products, 235.86769 atomic mass units. Now that's close, but it's not the same. There is a loss of mass. And this does not violate the law of conservation of mass because we put a clause in there, except in nuclear reactions. In a nuclear reaction, matter or mass can be converted into energy. So I think everyone's seen this equation before. E equals mc squared. So this is actually a very valid equation. The energy produced is equal to the mass lost times the speed of light squared. So we can calculate the energy that's produced in the fission of uranium-235. But I have to go back to see those numbers. So we're going to take the mass of the reactants, 236.05258, and we're going to subtract 235.86769. Well, a decimal point would be helpful there. So the change in mass there, if I did that correctly, is 0.1848. That's not an 8. 489 atomic mass units. So E equals mc squared. What is C? The speed of light. 3.00 times 10 to the 8th meters per second. What is a common unit of energy in chemistry? Joules. And a joule is equal to a kilogram meter squared per second squared. So if we use E equals mc squared, the meters per second on the speed of light are fine, but we would end up with atomic mass unit meters squared per second squared, which doesn't really mean much of anything to anybody. So we need to convert atomic mass units into kilograms. Any ideas? Moles would be involved, yeah. We could do it with Avogadro's number, or we could do it with the definition of atomic mass unit, which is 1/12 the mass of carbon-12 atom. So we could say that 12 grams is equal to 12 atomic mass units. No. We can say that one C12 atom is equal to that many atomic mass units. How can we find out the mass of a carbon-12? So here's where we want to go into moles, right? So if we have atoms, And we're trying to go to moles so that we can get to grams and kilograms. So 1 mole of anything is 6.022 times 10 to the 23rd things. And here, the mole of carbon-12 is going to weigh 12 grams. And then we have to convert that to kilograms. So 10 to the 3 grams in kilograms. So that number divided by 12 divided by 6.022 times 12 divided by 1,000. I'm getting 4.42 times 10 to the minus 28 kilograms. So the energy is equal to the mass, 4.42 times 10 to the minus 28 kilograms, which is a very small number, times the speed of light squared. And the speed of light is a very big number. So 3.98 times 10 to the minus 11 joules. Did I do my math right? Anybody? Then I'll have to assume I did. Let's see if I had the answer up there. Nope, didn't. I think that's not very useful. That's a small amount of energy, right? That's the energy produced by one atom undergoing fission. So what if we had a mole of uranium? Yeah, question?
I have a question. So you said the definition of for the 1/12 AMU. What was the definition of?
An atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. And there's some rather ingenious reasoning behind that. Because of that, the mass in grams of a mole of stuff is equal to the mass in atomic mass units of one thing. So if we took this number and multiplied by Avogadro's number, we're going to get 2.4 times 10 to the 13th joules. That would be for 235 grams of this undergoing fission. 235 grams is not a lot of stuff. You can hold it in your hand. Any questions? So we have a concept here called the mass defect. If we look at helium-4, and we look at that helium-4 nucleus, it has 2 protons, 2 neutrons. If we add up those masses, we get 4.03298. But the actual mass of a helium nucleus is 4.0026. So when we put those pieces together, we're losing mass, right? That's the mass defect. Where does that mass go? It's stored as energy. So all stable nuclei have this mass defect. If you do very precise mass measurements and you add up all the components, it equals more than the sum, more than the actual thing weighs because of this mass defect.
That doesn't sound right.
I know it doesn't sound right. That's why it's a defect. So that energy, remember mass can be converted into energy. That energy is called the nuclear binding energy. And that's the amount of energy that would be needed to break a nucleus apart into its component nucleons. It's separating all the protons, electrons, etc., neutrons. Nuclear physicists, I almost said physicians. Nuclear physicists often use the electron volt to report energy. As do students in Chem 1A in Chapter 8 who look up solutions to the worksheet. And I immediately know that they just looked them up online because this is the first mention of electron volts in Chem 1A. So an electron volt is the kinetic energy of an electron that has been accelerated through a potential difference of 1 volt. So literally an electron times volt. So we could talk about a mega electron volt. A mega electron volt is equal to 1.602 times 10 to the minus 13th joules. But the really useful thing here is this relationship. Yeah, that's good. Cross it out so they can't see it. If you do the math, 1 atomic mass unit is equal to 931.5 mega electron volts. So you can look at that mass defect for helium and you can convert that into mega electron volts. If you wanted that to be in joules, you could use this relationship to convert it. Of course, you can do the E equals mc squared thing as well, but these are just a lot more convenient. So the mass defect for helium-4 is 0.03038 atomic mass units. So what is the nuclear binding energy? Well, we want to use this guy right here, 931.5. So 1 AMU is 931.5 mega electron volts. So here's our mass defect. And this is just dimensional analysis with strange units. 931.5 mega electron volts for every 1 atomic mass unit. We'll keep with our 4 sig figs here, 28.30 mega electron volts. I'll give this to you on an exam, so you don't need to memorize it, but you do need to remember that it exists. So one thing we often look at is the binding energy per nucleon. What are the nucleons in a nucleus? The protons and the neutrons, right? So binding energy per nucleon is going to allow us to compare different nuclides. A larger binding energy per nucleon is going to be more stable than one that's smaller. So we could calculate that for this nuclide, 28.30 mega electron volts. And how many nucleons does helium-4 have? 4. 4 is the mass number. 4 nucleons divided by 4, we get 7.075 mega electrons. Yeah, that. MeV per nucleon. Okay, so calculate the mass defect and nuclear binding energy per nucleon in mega electron volts for uranium-238, which has a mass of 238.050,784 atomic mass units. Did I? No, I did not. So we need some more information here. Here we have the mass of the nuclide. We need to find out what's the mass of the protons and neutrons that are present in that nuclide, right? Which means that we need the mass of a neutron and the mass of a proton. Yay. And probably every semester I've said, oh, I should put that on there. I should make it just pop up. So here are the numbers that we need. So this hydrogen nucleus is a proton, right? So this is the mass of a proton, and this is the mass of a neutron. It's 783 and 866. Think I can remember that? Probably not. Did I do it?
Yep.
So this is the mass of one proton, and this is the mass of one neutron. How many protons does uranium-238 have? 92. So we've got 92 protons times 1.00783 atomic mass units per proton. And how many neutrons does it have? 238 minus 92, so 146. 146 neutrons times the mass of a neutron. So 146 times 1.00866. That's 92. 239, and let's do 5 decimal places. 98472 atomic mass units. That's the nucleus. So this is the actual mass, which is smaller. Because when these protons and neutrons come together, there is that mass defect. It's the nuclear binding energy. So we can find the mass defect by subtracting one from the other. So 1.933936. So the mass defect is 1.933936 atomic mass units, and we're going to convert that into mega electron volts. It's 931.5 per atomic mass unit. And then we're going to divide that by the number of nucleons. How many nucleons? 238. It's the mass number. start over. 238 nucleons. Okay, that number times 31.5 divided by 2. So 7.569 mega electron volts per atomic mass unit. That is not an exact number, so that's our sig figs, mega electron volts per nucleon. And this is our mass defect right here. Any questions? We pretty much guarantee there'll be a question like that on the exam for this chapter. So this is a graph looking at the binding energy per nucleon in mega electron volts as a function of the mass number. And so we see that hydrogen and helium have very low binding energy per nucleon. And as we increase in mass number, the energy increases. And we've got a maximum here at iron 56. Well, it actually maximizes it at 60, which is in here somewhere. So those would be the most stable nuclei. And this region here is where we see the difference between, is this going to undergo fission or fusion? So things that are larger than this yellow band here are going to split, and things that are smaller can combine. So if we break two heavy nuclei into lighter ones, that's an exothermic reaction. If we combine two light ones into heavy ones, that's also an exothermic reaction.
It says this also be
Yeah.